Right. So I actually used a data set that I don't know if Ken I mean, I would imagine I got this from Ken. I'll put it in the chat if any of you want to join the Zoom. That way you can catch the chat. It's like this. I think I might find it on. Oh no, I found it on Tidy Tuesday. I don't know if any of you follow Tidy Tuesday, but it's kind of cool because it's an interface where you can play with data and using tidyverse stuff, right? So I don't know if any of you are on Zoom, but I'm gonna put it in the chat here so you can see that it's a tidyverse, it's a Tidy Tuesday data set. Those data sets exist every Tuesday. In fact, tomorrow's Tuesday, so you'll see another data set come up. This is a very old from last year. But anyway, it's looking at like interesting things within different countries. So you can see that I'm going to obviously use tidyverse to read this. I probably have to first, I'm gonna put in my console here, tidyverse, because I, for some reason, have, I'm gonna disable the waiting room so anyone can join. For some reason, I seem to have, what do you call it? The tidyverse after I load the thing. Anyways, I probably should have had it this way, where you can see I have tidyverse here. Anyways, if you view mobile, you can see it looks like this. So what it gives you is the population growth in each country, as well as continent for a given year, right? So you can see that obviously you might wonder if there's a correlation between like over time and years and population growth. Maybe you think it will actually be trending in the positive direction. And maybe you think the rate of population growth is slower in certain countries than others. So if I try to draw a linear regression model, right, look at all the countries together and look at the overall global population growth, it might look scattered because population growth is going to change across different regions. So you're going to see me do a lot of things to data where I'm cutting and filtering depending on the region I want to look at, because population growth is going to change depending on where you happen to be, right? So perhaps I'm just looking at population growth, like total population in general. So if I just view for a second, if I view the mobile data, you'll see that. And actually, you can see that not only does it give you total population, it also gives you like mobile sub. I think it's actually mobile users per time, right? So you can see that in the early times, mobile users, for instance, let's say Afghanistan is not actually trending with population growth, because even while the population is increasing, mobile users in Afghanistan don't actually pick up until 2002. So you can see that you're not going to get, if you want to do linear regression for things like, let's say, population growth against mobile users, you cannot use that information in certain countries. So you have to really think about your question, right? So you don't get, for instance, mobile sub growth is a function of, let's say, total population in certain countries until 2002. So you can see that you just don't have that information in Afghanistan. It's like 0 up until 2002. So some things you just can't actually answer depending on where you happen to be. Anyways, let's suppose I'm curious about, let's say, total population and the continent, and then obviously year, like, is it right? So I'm going to create something called population, because you can see there are many features of the data set. It tells you mobile users, population growth, the country, the continent, right? So I'm going to pull up year, continent, total population. So if I just run this, you can see that I'm just selecting a couple. When you use a select function, of course, you're selecting across certain columns. Right. So if you can see that this is going to be just me selecting 3 columns. It's it's a very large data frame. It's like 3 by however number of columns there happens to be, but I've only pulled up 3. So if you look at tail of population, you'll get the remaining countries that you get like Europe, Africa, so you get different continents. Anyways, if I plot this, it's going to look ridiculous. How come? Because I didn't filter according to the population, the country of origin. I've just looked at all the population. And let's see what we get for the linear regression model. So the first step of linear regression is always to actually plot your data. So let's see what happens if I plot the scatter plot. What I get is something really ridiculous. I get this, right? Now, what is that? Actually, this is giving you the population growth for different regions over time. The reason why it looks like this is because you can see that the population growth for different continents is steeper than others, right? So for the 2 up here, which I suspect might be Africa and Asia, because I would imagine that population growth is bigger in those 2 continents than it would be in Europe or North America, whatever. You see that you have a steeper curve for population growth than you do in the bottom regions over here, which might be consisting of the other continents. What does this mean? So you can see that these are actually, this might even be countries. So this might even stratified according to country, because you can see that even though I'm pulling continents, there's more than 7 lines here. So it's entirely possible that even within continents, certain countries are moving faster than others. So you can see that this graph tells you not all countries experience population growth the same. And in fact, it's flatter in some of the countries. I would imagine in Europe and North America, the countries at the bottom where the population growth is flat is there, right? So this is the scatter plot of population growth according as a function of years. And you can see that it doesn't look consistent across the different countries. So if I was going to do a linear regression model, I'd have to subset and do a model depending on the country I happen to be in, right? You cannot just do a scatter plot for like this. You cannot put a line to these points. You can see that countries have their own population growth, right? We need to subset further. And in fact, you should actually have a country in mind you may want to look at. So you have to operationalize where you want to look. If you want to look at certain slopes. So I pull up Africa, right? But even now, so I filtered according to Africa. So this means I took population growth. And you can see that I filtered according to this. So again, so just to reiterate here, you can see that select will select across the columns, but when you say filter, what you're doing is you're selecting across the rows. In particular, you are selecting the rows that show like the continent is Africa. So you will not obtain Europe, Asia, South America, North America, etc. Right, so I filtered according to the row. So filtering goes across the rows, as you guys know. So if I filter and then do a scatter plot, what do I get? It still might look weird. You might wonder why that might look weird. It might look weird because it's entirely possible, even within Africa, not all countries are experiencing population growth the same. But you can see that this is what I get when I subset according to continent of Africa. I get something that's like, I guess I can look at the dimension to see how many observations are in Africa. You get 3, so there's 1,600, it's about a little more over 1,600 observations, so 1,611 observations. Now, if I do a scatter plot of this thing, you might wonder whether or not it's kind of, you might wonder whether or not it still looks like the plot above because you haven't really subsetted it according to countries. So you still have the same problem, right? So you can see that even within Africa, not all countries experience the same population growth. And especially because if you think about Africa, that encompasses the Horn of Africa, which is like, East Africa, but also has sub-Saharan Africa. And then it has like the Northern African regions where the people are ethnically more similar to Middle Eastern people. So you can see that you have quite a range of different countries. And that's why the lines still look different. So even if I subset according to continent, I still cannot put a line of best fit through these observations. What I can do though is, and actually you can actually see that in some countries, perhaps a linear regression model doesn't actually necessarily make sense, right? So in the countries in the bottom where the actual, where you can see that it's kind of flat population growth, you might think that the years are not related to total population in a linear model, right? So even if there is a relationship, perhaps it's not linear. You may not want to use a linear regression model, which is assuming a one-to-one map. Right, so if you think about in mathematics, the one-to-one map of like, Y and X, it may not even, while there might be a relationship in the countries down here, it may not actually necessarily be linear, right? So just because we put a linear relationship through an X and Y doesn't mean that there isn't some relationship. So there could be some relationship that is strong, but it is not linear, right? So you have to put a different line of best fit. Anyways, it appears we have different population growths within each country. So you have to actually, which means that in the beginning, when I was doing something like, view of population, I probably needed to actually, or not about this, view of mobile. I probably needed to also, I needed to probably put country as well. So there's something, I guess, coding for country. I think that's actually entity, right? So actually these two things are the same. So code and entity are the same. You can see that code is a short form for entity. So if you're looking at the data set and you're confused as to what that is, it turns out that code is actually a short form for entity. And if you just look at tail of like, let's say mobile, you'll see that Zimbabwe. So you can see that it's actually a short form, right? So you could choose either one. They're both complete and comprehensive. The reason why I chose Afghanistan, the reason why I choose entity is because sometimes when I want to plot it, at least it gives me the title of the country and the scatter plot, whereas I need to actually do an extra step with the other one. Anyways, so I probably should include that in my initial data frame. So I'll put entity there. Right, so now you can see that this data frame now consists of the continent and the entity, because we know that within each continent, population growth is not consistent. I feel like at some point I chose Afghanistan, if I remember correctly. Right, and so you can see that there's more things that could do to the GG plot. So you guys know whenever you evoke scatter plot or scatter points for a GG plot, you could actually put a line of best fit there. So you can use geom. When you use geom point, you can put geom smooth, and the smoothing will actually give you a line of best fit. But I'm not going to use that here because I know it's not appropriate because I have too many different slopes. I need to do something else first. So I'm going to first subset according to. I think I choose Afghanistan here. Right, so I don't know why I did. Probably when I was looking through the data, I noticed that it had a very steep curve, and that's probably why I used it. So you can see here that I'm going to, I mean, another data set here. So anyways, I'm going to run this here. And actually, I think at the top here, I'll probably remove the entity because it seems as if I made a different data set, right? Added entity down there. So I'm going to move this here. Anyways, if you look at the scatter plot, so Ken is going to give you a code, obviously, where you can put the line of best fit to your GM point. That's GM Smith. But you also will learn about the LM function. Have you guys learned about LM function yet this week? Not yet, right? You did, right? Okay, so you'll see the LM function, and that is linear model. So not only will you plot it to see if this is what you see, but you'll do an LM model. Now, at some point, you'll probably talk about the p-value and whether or not your model is significant, because just because you put a line of best fit doesn't mean it's a significant model, basically. So let's first look at what we get. Let's run it. So we'll see here that, hey, where's, oh yeah, here we go. This is actually a pretty good line of best fit. So you can see that there is a pretty strong linear relationship between, so there's a pretty strong linear relationship for Afghanistan population growth across the years. It looks like each year there's a linear growth and the rate is constant, right? So obviously, you know, if the growth is linear, then that means the rate of growth is constant, like it's constant each year. But you can see that it's pretty good, right? So this is a pretty good line of best fit for Afghanistan. Now, obviously, I put centered area equals false. If I remove that, it's going to give me the confidence bands. And really, you should look at the confidence bands to see how good your model happens to be. If I put the confidence bands back, you see that it's actually really quite good, right? So this really actually is governed by a very strong linear model. Most of the points are directly on the line, except maybe you have a couple of chatter points over here, but it's doing a pretty good job, right? Now, that's not going to be true for all the countries. You may find in some countries the line is actually constant across the years, meaning that the population growth is not actually directly related to how many years the country has been has been a republic or whatever, it's been in formation. So I'm going to do a LM model now, and let's see what we got. So so this is actually LM. You can see here that I have total population as a function of year. So when you have something that looks like Y squiggly X, this is me saying that the actual response variable here is total population. And I think that it's a function of year, right? So it's Y is a function of year, and then I'm going to put in the data frame. So this is, keep in mind the order you have here, because whenever we grade these assignments each year, students mistakenly interchange X and Y. If you put year here and total population, you're saying X is a function of Y. So you have to think carefully about what your actual response variable happens to be. That will influence, that will surely influence your covariance, right? Because when you're saying, and actually you can for yourself logic out what should be Y and what should be X. If you think about like which particular variable has the least amount of variability, that is going to be the X variable, and the Y that can change a lot is the Y variable. So you can imagine years is pretty fixed. Years is something that's immutable. The population growth is variable to a lot of factors. So intuitively, you know that population growth is the y variable because it's variable. There's a variability according to a certain number of factors, and then years is immutable. So if you're ever confused as to even any time variable is going to be an x variable because you cannot influence time. Time moves whatever you do, right? So you would probably intuitively know that the y variable is the other thing, right? Okay, so now let's look at our model. I called it Model A because obviously Afghanistan. So if I look at, if you want to look at the summary, you run it. If you do Model A into the console here, you will just get this, right? It will tell you the coefficient. So it will tell you the intercept terms because you know that the model is governed by the following. So you know that the model looks like, you know, y is equal to, you know, mx plus b. I should put y hat, right? So this is obviously the intercept. And then this is, you actually really care about this. Because this m here tells you the way in which y and x are varying. So you actually only really care about m. It doesn't really matter if the intercept term is significant. That's not the thing we're interested in. But you can see that if you put in the Model A into the console, you won't actually see significance. You have to do summary of your model to get more information. Now, if you do this, what do you actually get? You get a lot, guys. Notice that you will get the intercept term significance, which we don't care about. You get the significance of the year, right? So first of all, you get this significance. So I'll talk about this in a minute. But you get the estimates too. So what this is saying that this model is governed by the following. So your model is actually, you know, this is actually equal to minus 1.721. It's actually kind of, you know, times 10 to the 9, I suppose. It's kind of a big thing, right? So it's kind of big. And then this one here is, you know, 8.720 times, I think it's 10 to the 5, if I'm not mistaken. It's a pretty big, right? So this is what you get, right? So you can see that it makes sense that notice that the slope term is positive. That makes sense because your correlation is positive. Whenever you have a positive slope, it means that whatever the relationship is between x and y is trending in the positive direction. Right. So if your slope was negative, it would mean your line of best fit would actually be negative. Like you see that as your x is increasing, your y is decreasing. So I guess you see that here if you run this, as x is increasing, y is increasing too. But if you saw the opposite trend, your slope term would actually be negative. This is something to note, right? So you can see that the sign of your correlation is showing up in your slope term. A negative correlation would indicate that as x is increasing, y is decreasing, and you would see the opposite thing. You wouldn't see this line going this way, it would be going downwards instead. But I want to point out a couple of things in this thing. Notice that you have been working with paired t-tests for the past, and even t-test for independence. This is a one sample t-test, right? So you can see that your actual output is a one sample t-test, right? So you've been doing this for a while, but what you actually have here is a one sample t-test, right? And it's giving you your actual t statistic and the p-value for it, right? So notice that your t statistic for year, which is a slope term we're interested in, is actually 49.41. So you actually have t is equal to 49.41. Now what is t? T is actually equal to, right? It's actually your actual mean you saw in the population minus your hypothesized mean divided by S over root n. You guys know this. You hypothesize that this, now because you're actually trying to test for significance in your coefficient, what does that mean? There is no relationship between x and y so there's no relationship, x and y are independent if, you know, beta 1, which is your slope term, is 0. If your actual slope term is 0, it means there's no relation between x and y. Right, so because you want to actually show there is an association, if you think about this, your actual test of significance is the following. You assume that you actually have no relationship, but what you really want to show is that there is a relationship. So this is the hypothesis that you're performing. You're performing the test for significance where you want to actually show that your slope term is not 0, right? So if you put the model, your model actually looks like this, you know, it's beta naught, you know, plus beta 1x. Right? What you actually really want to show is that this term here, which governs the relationship between x and y, right, is not 0. So you really want to show that this is not 0. right? Now, obviously, it's not zero as long as your correlation between the two things are not zero, right? So we can see from our plot that obviously it's a pretty strong correlation. And in fact, the t-statistic we get is this, which means that if you actually plot this t-statistic, so if you were to actually plot this, right, it looks something like this, right? So you can see that this is the null distribution. It's the null distribution, right? And if your null hypothesis is true, then t is equal to y bar minus mu over s divided by root n is actually equal to 0 if y bar is equal to 0. So you can see that t is equal to 0 is directly here, right? Now your test statistic is like something over here. It's like 49.41, which is really far from 0. Notice how the p-value actually shrinks when you go further into tails. What is it actually saying? It's saying that if the null hypothesis is true, the odds of you seeing a test statistic so big is like 2 times e to the minus 16. So it's like almost 0% basically. So if the null hypothesis is true, the odds of you seeing a test statistic that far into the tails is very unlikely. So you can see that for your test statistic, you have a p-value that is almost 0. So you'll actually reject a null hypothesis. And what does that mean? It means you're going to conclude you have a correlation between population growth in Afghanistan and the number of years. That as the years increase, it seems as if there's a significant increase in the population growth. And so make sure you always answer within the context of your data. So you get, again, you get a couple of things. You get the actual line of best, but you also get the significance. If you get an assignment question, and you can see that the p-value is kind of not significant, it would mean that even though you have a model that the output gave you, it is not significant. And if your p-value is bigger than 0.05, what it means is that your model is actually null. The null model is the model where you just have this intercept here, and that this is actually 0 because there's no relationship, right? So we're interested in not only finding the coefficient, we're interested in 2 things. One, estimating the coefficients, but we also need to know if they're significant, because if they're not significant, of course, that would insinuate that we have the null model, right? The model where you have no correlation between x and y. And just something to keep in mind. Now, the thing I want to point out here, now, I actually didn't really do what the data wanted me to do. The data wanted me to look at the mobile users. I was looking at population growth, but if you are interested in looking at mobile users, you can do that, right? So let's suppose I want to look at mobile users. Let's see here. So what did I create here? View mobile 1. Yeah, so you can see that if I'm interested in mobile users per year, right? What I'm going to select here, obviously, is the country, the continent, the year, and the mobile subs, basically. For Afghanistan, you probably wouldn't want to check the mobile users before 2002 because they don't have any users, right? I think I did pivot. If you look at the original data set here, notice that it has it in long format. If you look at, you see the original data set has things in long format, right? Each year, it shows Afghanistan, and it's showing each year, right? So it has now this is wide format, right? So this is wide format. You can actually see how this is this we call wide format. So if you're ever curious as to how to almost transpose your data set, because maybe you want to, for instance, you just want to get people in Afghanistan who are mobile users for each year, and you want to do some kind of visual statistics on it, you can do pivot wider, and actually you can see that it changes from wide format. This is the original data set where it's doing things in long format, but here is the wide format where you can see that for each country, it transposes your data set so that you have each year displayed like this for each country. So this may be relevant to you. Why is that? Because if you want to do some summary statistics, you can see it better in wide format. So for instance, you can see that in this country here, Angola, I guess, there's actually no mobile users. And in fact, there may not even be any data. Notice it's NA entirely. This gives you a way to remove certain rows. You don't want to move certain countries you realize have no information if you want to address your question. So if there's any countries that doesn't have any information, you can cut it out by looking at like things in wide format, right? So this is me giving you kind of a couple of tips right? And then because we're out of time, I guess I'll just say quickly, if you wanted to select variables if you want to select variables, you use select. If you want to select observations, you use filter, right? So if within mobile 1, I want to select people in Asia, because I have Asia select, because my Asians now are selected in the row space here, I can filter in this way, right? So you can see that because I have things in wide format, I can actually select people who are select countries in Asia, right? And then if I just run this, you will see that my data set just consists of, oops, what did I do? It just consists of, mobile users in Asia in 1991, for example. Maybe you have a particular year you want to look at. So I'll just let you play around with this. But obviously, if I just remove this, if I remove this thing here, and I just have this, I will get users in Asia. So if I just view Asia, I'll get all the actual years. If you want to look at a particular year, so you get all the Asian countries. If you want to look at a particular year, you can add certain features. So I put 1991 out of curiosity, but if you want to look at a certain year, you can do that as well. The tutorial's over, but I did put a couple of other notes in terms of merging, because I think in this tutorial, Ken does actually ask you to do, not only does he ask you to do linear regression model, I think you actually have a lot of tidyverse things if I remember correctly, in this assignment, where you might be doing merging and a lot of left join stuff. So be careful here. Please read this part carefully. In your assignment, he does actually, I think you may actually do left join, right? And if you choose wrong join, you may get a different data set than what you're supposed to. So have a look at this. I'll post this on my GitHub. And I'll also record, obviously, the 10 tutorial as well, so you can have a look and see. But you will see that he may ask you to do things like left join, and you may get the wrong data frame if you didn't use the right join function. So something to look at carefully before you try your assignment, because I think each year I get and even the order in which you actually do the actual joining matters. If what X and Y happens to be matters. So be a bit careful about this, because I think each year there's always a couple of mistakes in the assignments, but try not to let that be your mistakes. If you just read this carefully, you will not be the one that turns in a slightly incorrect assignment. But that's it. I'm going to pause the recording, and hopefully. So I put this is a tidyverse, so I'll actually just show it to you guys. This is actually a Tidy Tuesday. I don't know if any of you have heard of Tidy Tuesday, but it's this thing where people have an opportunity to play with data that's posted online by someone who, it's like a competition each Tuesday that happens with data. You can see here that this is a CSV file that's online that you can get from the Tidy Tuesday repository. And in fact, each Tuesday they have a new data set. They even have one tomorrow. Oh, sorry. This is not right. You can see that each Tuesday there's a repo for Tidy Tuesday. So there's another project that's going to come up tomorrow. I pulled up one. This is from last year. Or if any of you are curious, it's really a way for you to interface with the tidyverse universe, because you start using operations in tidyverse. Anyways, this is data pertaining to mobile use across different countries, and trying to see how it relates to population growth, basically. So you can see that if I run this in R, what I'll get is the entity, which is actually the country of origin, the year, the population growth, and then mobile subs. You can see that even though the population is growing in certain countries, it's not necessarily true that people are using mobile apps yet. So in Afghanistan, for example, mobile subs is not actually a thing. It doesn't ping until 2002. So, and in some countries, you don't get any mobile use. But anyways, I want to use this for a couple of reasons. One, you will see that you cannot just blindly use linear regression without thinking about the features of your data. And then two, it lends a good hand for tidying. Because I think in this lab, you will be doing tidying, or you'll at least be using left join, which is an SQL sequence. If any of you are in computer science, you'll see that it's an SQL thing that allows you to merge data sets according to a particular operation basis. So left join versus right join versus inner join doesn't give you the same data set when you merge them. That's a feature in SQL, but it's also a feature in tidyverse as well. Okay, so maybe I'm interested in looking at population growth across the population, across the continents each year. So what I really should have called this is probably continent. But anyways, you can see that if I want to know how the population is changing across the years, maybe I want to do a GG plot where I'm looking at like, because you might imagine it's a linear relationship, but that it's increasing linearly with each year. So I pulled year, continent, total population. Select allows me to select across the column space. So I'm selecting 3 columns. Of course, you can see in your actual data, there's more than 3, but I'm going to pull 3 out of the 7 basically. So let's see what happens if I do this. What I get is something. Let's see. Oh my goodness. Okay. So you see that I will get this. So if I view my data, so you can see that it's actually a data set with just 3 different columns, but it gives me the year, the content, and total population. So I'm going to see if there's a linear relation between population growth in the year, where I'm thinking that maybe it will increase as the years are increasing, basically. So if I do that, what do I get? So I'm going to put this data set here. What you see is this, which is a little crazy. What it actually shows is that the population growth is not consistent across the different countries. In fact, you can even see that across certain countries, the population growth is kind of flat. We might speculate this could be countries in the Western Hemisphere where population growth is not very prolific. But you can see that it's not equal across the different regions over time, right? So we cannot just blindly apply linear regression to this scatter plot because the population growth is not consistent across different things. You can also see that there's actually more than 7 different lines, which insinuates that I actually have, this is not actually stratifying according to continent, it's stratifying according to country, right? It isn't like you can see certain countries in the data set. And if I even look at unique, let's see, if I just attach, I can even see, so if I attach mobile, it will see that, so unique entity, let's see, oops, unique. You'll see that there's 247 unique countries, which probably means that there's actually 247 of these lines basically. It's actually not stratifying based on continent because there's more than 7 lines. It's doing according to countries, suggesting that some countries have bigger rate of population growth than others. So which means that maybe I need to actually subset further. So I then said to myself, okay, let's look at just Africa, and I can actually filter based on Africa. So notice that in the initial code, I was selecting columns, right? But if I filter, I'm actually filtering according to a condition on the row space. So if a particular continent is not Africa, it will not select it, right? So I'm here, I'm subsetting based on Africa. So if I run this, I should get just a data frame that is going to be less. So if I look at the dimension of, let's say, mobile, which is my original one. So if I look at the dimension of population is actually going to be 6,277, but the dimension of Africa should be something below 2,000. So it's 1,611 because there are less people, right? But anyways, if I plot this, maybe this will give me a linear line that I can do a line of best fit on. When I do that, I still have it. So initially what I have is this. I still have the same problem because there is many, so if I look at the unique entities in this data set, so entities are countries. We will see that, oh, I actually don't think I actually did that. I didn't actually pull it. So this data set doesn't actually, this is a limitation, but in my initial data set. The initial data set does not actually contain entities, so I'll address it later on. But you can see that there's actually multiple unique countries in Africa. It's just that I didn't include entity in my first data set. That's why I couldn't actually do it. See, the initial data set I actually only had constant. I did not put entity, but I'll address that in a second. If I do the following, basically, unique. If I just add this in, I can check and see what that is. Let's put this in. If I just run this, I can see. Now let's look and see. So let's see how many unique countries there are. As you see that stratifying it based on continent didn't solve the problem because I still have too many countries within Africa. So, which means that if I look at the unique entities, you'll see that there's almost 60. So you will still see too many lines here. There's about 60 of them because the population growth is not consistent across 60 different countries, right? So that's not, we have to do a bit more work here, right? So instead, I'm going to filter across a particular country. Now, the reason why I actually chose Afghanistan instead of choosing a country within Africa is because their population growth is actually pretty linear. If you look at their population growth across time, it looks pretty good, which I was kind of surprised. I didn't know that because there's a lot of external factors in certain parts of the Middle East, but it turns out that has not influenced their population growth. It's still a rate of change that is constant. So that was kind of neat. So I made a new data frame that now includes entity because the initial one did not. And then because now it contains entity, I can actually filter according to country, whereas I could not in the initial data frame because the initial one only really contained, if you look at the view of the initial one, it only contained a continents. Or actually change that, sorry. The initial one should have only contained continents. So really the initial one here, it only contains continents. So I could not filter according to the country. But now I can because the second one actually does contain, my set does actually contain the entity. So now I'm going to select Afghanistan, right? So that means that because I'm filtering across the different rows, because I want to cut out rows and not Afghanistan, that's filter, right? So if I run this, you'll see that if I view this, what I have is, let me see. You have this, right? So you can see that these are only like, this whole data frame consists of 28 observations. That is Afghanistan, right? That's 20 different years basically. Ironically, you don't actually have the population size for these years here. So you want to imagine they're getting bigger. You can actually see it. So when I put this into the LM function, it's going to actually cut out those observations. So there's 4 of them you don't have, which is kind of a shame because it's in the higher years. But you can imagine that because it doesn't have those 4 observations, when I put that into a linear model, we'll actually cut out those observations, right? Because it's not there. Anyways, let's look at if I just run this plot here without putting GM smooth, it looks pretty good actually. So if I just show you guys this, you will see that this looks rather good. I mean, like it's not, there's certainly a non-linear thing, but it's pretty, you can see a pretty strong trend. As the years increase, it looks like the population is growing. So I probably could put a line of best fit that is linear through this, right? So the first thing to do whenever you want to do a linear model is always to put a scatter plot, right? You have to make a scatter plot to see what you're working with basically. If it doesn't look linear, it doesn't mean there's no relationship. It just probably means you shouldn't use linear regression model basically. Anyways, if I put the smoothing thing here, what do I get? Actually, I wanted to put standard error equals false first. Yes, C equals false. So I'm removing the standard error so you can just see the line first, and I'll put it back. So you can see that this is the line of best fit I get, which is pretty strong. So this is a very strong linear relationship. There is some chatter over here, obviously, but it's doing very well over here. You can see that it does tell you there are 4 rows that were removed because like I showed you in the data set, there is no points over here. So there's nothing to extrapolate. It cannot extrapolate when it doesn't have the line of best fit. Or it doesn't have the points basically. Anyways, you can see that this graph is lacking in something. What it's lacking in is it doesn't have the standard error bars. without the standard errors, you actually don't know how your model performed, because everybody in this course should have taken B57. And you always have the interval and the point estimates. You cannot just blindly, put a line of best fit without knowing how wide your confidence band happens to be. A very wide confidence band would indicate your model didn't do very well. So I'm going to remove the standard error equals false, so I can put it back in and show you guys what I get. So if I do this, if I run this, what I get is this. So in fact, even the confidence bands are pretty tight. This is a really good fit, guys. Notice that you get these blue, you get this gray bars around the blue line, which is the standard errors, but it's pretty tight. This is a pretty good fit. And we can confirm this when we use the LM function, which will give you the linear model. As you can see, it's doing a really remarkable job, right? Where most of the points are on the line, and the standard error bars are pretty tight, meaning that the range in which it estimates is pretty narrow band. Now, it didn't do very good over here, obviously, because you can see that the confidence band doesn't contain the true values. So it will tell you that it will underestimate your values for these 3 points here, for these 5 points here. And it will, I guess, it will underestimate here, and it overestimates over here. So there's a couple of points of contention. You can see here it actually underestimates, right? Because you can see your actual standard, your confidence interval doesn't contain your three points here, which are the true values. And then over here, it doesn't contain 5 points, but for the most part, it does a pretty good job. But yeah, there's a bit of a problem here and here because your interval will not contain your true values. But anyways, let's put the LM model. I want to show you guys a couple of things because you will run this, and probably Ken may have already ran this. If you put model A into the console, what do you get? You get this. Right now, this gives you a couple of things. It gives you the intercept term and the slope term, because you guys know with a linear regression model, what you actually have, I'm going to do the following. I'm going to use a different thing. You have y hat is equal to beta naught plus beta 1 x I, and this is actually the intercept. And this is the slope. Now, obviously, we are interested in the significance of the slope term. In fact, we don't really care about the intercept term at all. The only thing the intercept term gives us is a way to predict, because the whole line itself is a way to predict a value for a given value of x, but we don't really actually necessarily care about this at all. Okay, so we don't care about the intercept term. We are focused on the slope term. I will say that this term is significant if you have a high correlation between x and y, and you can see sometimes pictorially, if you have a weak relationship, this may not be significant. The null model, guys, the null model is actually given by, it's y is equal to beta naught plus your error terms, right? This is the null model. The null model is actually the model where you have, I should write this bit. You have like you just have your error terms, and you have the intercept. And the slope term is 0. It implies that beta 1 is equal to 0, meaning you don't have a relation between x and y. Now this is the null model, right? So this here is a null model. Obviously, we don't want the null model. We want to show that we can predict the population as a function of x, but you have to check this. You can't assume you have, just because you get estimates in R, does it mean that your actual model is significant, right? You have to check. So this is why when you put in this into the console, well, it tells you something. It doesn't tell you everything. You can see that it does tell you that it does tell your actual line of best fit, in the sense that I can say that this is going to be something like, I can say that the following is true. The y hat is equal to minus 1.7 to 1 e to the, I guess, I think it was 9, was it? Yeah. Which is like 16 to the power of 9. It's a really big number, right? Plus, I think it was 8.7 to 0 e to the 5. So it's like saying 10 to the 5. It's a really big number too. X, right? X is population, right? Notice your slope term is positive because your actual ggplot here is positive, right? You would not have a negative slope term when your scatter plot shows a positive correlation, right? So the only way you would have a negative slope term is if your correlation is negative in the sense that like as x is increasing, y is decreasing, and it's increasing, sorry, as x increasing, y is decreasing. And then your graph would show the opposite. Instead of going up like this, it would go down this way, right? So that's really the distinction there, right? What I do want to point out is that this doesn't tell you significance, right? So if you just put a model into your console, you will not get significance. You have to do summary. So you need to do a summary of your model to get the significance, because notice that you get more things in the summary. Not only do you get your estimates, you get the t value that is associated with your estimate. Now, you guys did do t values in this course. You did a one sample t-test, and this is what this actually is. This output in your R is actually a one sample t-test, whereas performing this test here, right, where you're trying to assess if your beta 1 term, which is the slope, is 0 or not. Now, obviously, intuitively, you do not want it to be 0. You want to have this alternative be true, which is the research question, because you want to say that as the years are increasing, your population is increasing, and it's explained for by how many years Afghanistan has been a nation, basically, right? But that doesn't necessarily mean it's always going to be significant. You're actually doing this test here, where you're looking at your actual mean estimate in your sample, and this should actually be beta. Right? So this should actually be beta 1. So what this actually is the following. It's beta, it's the mean for beta, so it's your actual estimate beta 1 hat minus your hypothesized one, which is in this case is 0. This is actually going to be 0. And the question is this ratio between beta 1 and, if we're being very particular here, I guess we could even be like formal here. And we can say that it's actually this. It's the standard error for beta 1. So this is the test you're actually doing. It's a t-test where you're looking at your actual estimate minus your predicted one, you're dividing by the standard error. Every t-test looks like this, where you take your actual value, which is beta 1 hat, in the sample, and you subtract your mean value, which is going to be 0 in your hypothesis, and then you divide it by the standard error for your beta 1 hat. Actually, it turns out you can actually show this yourself, right? So if it's the case that x and y are independent, then you will find that this beta 1 term in your actual R code will have a p-value that is not significant, right? So if the null hypothesis is actually true, when we look at the actual beta 1 term, the p-value for it will not be significant, right? Now, what I want to point out is that you can actually compute this yourself, right? So you can see that while the code is actually telling you the t-test gives you a value of 49.41, on the other hand, you can actually compute that yourself. You can actually see that it's true, right? Why is that? Because t is equal to beta 1 hat minus beta 1 over s of beta 1 hat, because that's how every t-test looks. It's the mean you saw in your sample minus the hypothesized mean divided by standard error. Now that is actually 8.270 e to the 5 divided by the standard error here, which is 3.533 e to the 7, right? Is that right? E to the 7. No, e to the 4. If you do this in your calculator, that actually ends up being 49.41. So that is how you got this code here. So it's actually doing a t-test. This is a one sample t-test. It's doing the t-test in R. And this output is a one sample t-test, right? And here's the p-value that is associated with that t-test. Now, what does that actually mean? It means that if you actually draw your null distribution, your t statistic is somewhere in the tails, right? So somewhere in the tails, like maybe somewhere over here, right? which is associated with a very small p-value. Now, whenever you have a t statistic that's in the tails, what it's actually saying is the probability of observing a test statistic that is that big, if the null hypothesis is actually true, right? So if it's actually true that beta 1 is equal to 0, which is somewhere over here, you should not have seen a test statistic this far out unless you truly actually have an association between x and y, right? So if there is no association, you should have seen a p-value in the center of the distribution for the null. Instead, what you saw was your p-value was over here, which is indicating that the oscillations are pretty unusual on the null. Now, in this instance here, we will actually reject the null hypothesis, and the conclusion will actually yield is that there appears to be an association, at least in Afghanistan, between how many years it's been a nation and then the population growth. And then the rate of change appears to be constant each year, and it's leading to an increase in a linear increase in the population growth, basically. Which we kind of expected anyways, looking at the scatter plot here, it's trying to show us a linear trend. Now, if I were to actually be a bit more formal, I might say that maybe we would trust the results a bit more in later years, that we might be skeptical in the earlier years. If I was going to submit this for publication, I might say that perhaps you could take a closer look at what's going on over here, obviously, because it's doing a pretty good job here, but there's a problem over here where the confidence bands are missing the actual values. But anyways, you always want to make sure you run the summary so that you can see the significance of your coefficients. Now, the other thing that you might actually notice in this assignment that comes up is you're going to be doing a lot of left, like inner joins and stuff. And I'm going to go down, just in interest of time, I'm going to show you guys something over here, because I think that this is actually, I talked about this, and I posted a recording, and I'm going to post a recording, and I discussed this in the previous tutorial, so you can watch, but I want to show you guys this. I did not cover this, and I think this is on your assignment. Merging in tidy. You guys will actually see that he might actually ask you to do a merging of your data, like a left join. I think if I remember last year, you guys the class to do a left join. So I suspect you might do it again this year. But the thing is, you can actually see that the join you do might result in different data sets. So it's really important to make sure you're clear about this and look and see what your data set created. Don't just do a join and leave, because there are 3 different joins in tidyverse and they don't all do the same thing, right? So and you have to think about what the question's asking you to determine which join sequence to use. You will find in the tidyverse page, and I guess I can pull it up for you guys. So tidyverse. There are a couple of, yeah, so I guess I can, yeah. See here, I'm going to put this, I'm going to show this page. Maybe I'll just, it's this page here, because I guess I realized I'm only one in Zoom chat, but anyways, this is the page. Maybe I'll put in my file before I post it on GitHub. But anyways, it does tell you the definitions for each of the different things you're doing when you're mutating your data set, right? So inner join returns all. So if you do inner join, what is that? Well, from the tidyverse thing here, I will show you what that is. Where is inner join? Where is it? It doesn't have a good definition, does it? Anyways. Inner join includes all the rows in X and Y. That means that when you are trying to match based on a common key, you always have to match based on a common key, which you can see that it may give you the inner join may give you the most amount of rows, because it will take all the rows in X and Y and combine them in some way. Even if there is an X pair that is missing a Y, or a Y pair that's missing an X, it will include those rows and will leave the missing X and missing Y blank. So you will get the most rows in inner join because it will include all the possible rows of all the possible combinations of X and Y, including the ones that don't have pairs, and then it will just leave them pairless basically in the data set. So if you want a complete data set where you have pairs for X and Y, you may not want to use inner join. So you need to think about what your question's asking you, basically, right? So again, inner join will include all the rows of X and Y, even those that don't have pairs. So you will get the most number of rows when you use inner join, basically. But left join versus right join, it does something different. So left join will include all the rows in X, but not necessarily in Y. So if Y does not have an X pair, it will not include that Y row into observations. But right join will include all the rows of Y, but will not include X. So if there's a particular X that does not have a pair with Y for right join, it will not include it, which means that the features, you will get different data sets depending on what you specify as X and Y. So please make sure you're careful about this. I don't think I've ever thought to myself what the difference is between inner join and full join. I need to see, because it looks like inner join and right and full join contains all the rows in X and Y. Maybe the distinction between inner join and left and full join, because I think full join's a new one. I think that wasn't there last year. I think they added a new feature. So I don't know what full join is yet because I haven't worked with it. I think it's new. I suspect that full join might be the same thing as inner join, but it just depends on how you permute X and Y. But I need to check and see because that wasn't there before. I think they included it recently, which is kind of neat, I guess. I have to look and see. Tidyverse always updates itself. But anyways, let's see how this works. Right, so because the tidyverse does not have a comprehensive list I included more things. I said that I made more notes for myself here in my GitHub, so you can kind of see that. You can see that all the combinations I put here that all the combinations are returned for inner join. But with left join, if there's no match, if X has no match with Y, because the left join is actually going to include the rows of X, it may not actually include your Y, basically, right? So be a bit careful, they're not the same. So I pulled out a data set from Tidyverse to show you what's going on. This is the data set in Tidyverse. It just has 3 rows. It has Mick. So it's just an artist name and then their band. So I think Mick Jagger is in Stones, John Lennon, I guess, Beatles, and then Paul McCartney, Beatles again. So you can see that this is a data set in Tidyverse. So it will not actually load in base R. If you try to load band members in base R, it won't actually load until you first call the library Tidyverse. Anyways, we also have a data set called band instruments, which includes includes the instrument they played. So John Lennon played a guitar, Paul McCartney played a bass, I guess, and then Keith, I don't know that maybe it's Keith Knight or Keith Legend. I'm not sure. I think these are well before our time. He played guitar basically. Whoever Keith was, I don't know who Keith, because I think that might be a bit before I was born. So I don't know. I don't know who that is, but anyways, whoever Keith happens to be, he played guitar. But notice that Keith is not in the first data set, right? So Keith is not in the first data set, right? So that means that that's going to have an implication to your inner joins, basically. What happens if we use inner join? Let's see what happens. So notice I'm saying that X is the band members, and I want to append band instruments. What do I get? You'll get this. So you can see that you will see that you get different things depending on what your X and Y happens to be. So here, I get John. You will tell me that John is a Beatles member who plays guitar, and Paul is a Beatles member who plays bass. But Keith is not in the initial data frame, so you don't get anything about Keith. But now, if I change the order so that band instruments is actually X and Y is band members, I get something different. Let's see what we get. You get. How did it? That should have been 3 by 3. What happened? So weird. Let me see. Oh my gosh, this is interesting. The code updated itself. Let me see something here. Yeah, okay, cool. Okay, so you can see here that you get all X and Y pairs, but Keith is not in the initial data frame, which means that he was removed. And in fact, you get the exact same, you get the exact same data frame, right? So here you get the same data frame here, albeit I think the order is a bit different. See here that the order is different because here you specified X was actually band instruments, right? Here you specified X as band instrument, here you specified X as band members and Y as band instruments. Here you specified Y as Y as band members instead this time, and X as band instruments. So it depends on what you specify as your X and Y, right? So this means that the first one is doing a Y to X, and the second one is doing X to Y, which is why you get different orders for the actual columns, but it gives you the same data frame here. However, when you do a left join here, you will get a 3x3 tibble. It will look a bit different, right? Because you can see that it's taking all the columns. So you can see here it takes all the if you have missing Y observations here, so here you can see it's doing Y to X. But if you have missing observations here, so for example, you can see that Keith is missing a band. Keith is not in the band data frame, right? So if you think that there's missing observations and you want to fill it in, so you might do a left join, because left join, remember, is actually includes all the rows. It includes all the rows of X basically, right? Now, if you think that you have missing observations and you want to include it, you might do a left join because it will give you an NA and you can fill it in basically. Now in this example here, we could actually fill it in by looking on Google basically. So again, if you suspect that you want to include an observation that's missing, if you want to include all your observations and there's missing data, you want to fill in yourself, you might do a left join because inner join will include all the combinations of X and Y. And that means that if X and Y don't have certain pairs, it will omit it basically. So inner join includes all the combinations of X and Y that exist. But the problem is inner join gives you the most comprehensive data set where all the pairs are actually there. It will not give you NAs. If the pair is not there, it will just cut it basically. Whereas you can see that if you use a left join, it will include observations where there's missing data, and you can fill it in yourself. Because we can actually fill this in if we Google it, which is why it might make sense here, obviously, to include the NA, because this is something you can Google to fill in your data frame, right? So we know that Keith belongs to some band. If we Google it, we can figure out which one it is. So sometimes when you want to actually include observations that are missing and don't have pairs, you might choose to use a left join basically. And I think in your tutorial, I think in your assignment, I think Ken does actually ask if you use a left join, I'm pretty sure, not an inner join. I think you asked to use a left join because it gives you more observations. So I think in your assignment, I don't know if it's this year, but last year was a case that the function you guys were supposed to use was actually a left join. I don't know if there was missing data in the data frame, because I forgot, but you can see that left join does give you all the positive values of Y, because that's what it's supposed to do. Because again, left join is supposed to include all the values of Y, even if they're missing basically, right? So you can see in the initial data frame here, in band instruments, there's a missing, in band members, you can see that, of course, Keith is missing, he wasn't in band members, right? Which means that you will get a missing blank if you use left join, because it's running across the values of Y, right? And Y is obviously band instrument. So you can see that it will give you Keith, but it will tell you it's missing. If you do right join, what you will get instead is you will get John, Paul, and Mick instead. So if you use a right join, you'll get John, Paul, and Mick. But when you try to do a join with the band instruments, you will see that Mick is left blank. Right. So again, so I'm just saying it's homework because you'll see this will have some implications. So for homework, if you do right join, you will see then Mick will feature with an NA instead of Keith. That's because we don't know, it doesn't tell us what instrument Mick played. We can Google it up basically. We would not know what instrument Mick played. And that's because now you've made Y to be, you're including all the columns of X, and X happens to correspond to the band members. X will correspond to the band members, yeah. And because you don't know what instrument Mick played, it will leave it blank basically. So please check Look and see in the assignment what Ken specifies as y. This will have implications as to what exactly you should, what exactly your data, what you should use for your data frame, basically, right? I'm pretty sure that's in your homework, and it might even be in your homework. It might even be something you have to do before you do your linear regression model, meaning that if you made an incorrect data frame, you may get an incorrect LM model. So check that first, right? So if you're supposed to tidy your data first before you make the LM model, please check and make sure that you're being a bit consistent about this, right? To ensure that you don't have that mistake, right? So just my last example here, I did another LM model here because I always use the MT cars. I think I've used it in every tutorial, so it's fitting that I use here. I want to check the linear regression model. I just want to point out that this is something to check as well. This is a common mistake people make. Please check what X and Y happens to be when you put it into your LM model, right? So here, if I put MPG as a function of weight, I'm saying that I think that the miles per gallon is a function of weight. That means that what I'm actually doing is the following. I'm saying I think that MPG is equal to weight. So it's equal to, beta 1 weight times weight plus a beta naught, right? Plus maybe some error terms. That's what I think the model happens to be. So you can see that I'm saying that the Y variable is actually MPG and the X variable is this. Please check in your assignment which is X and Y, because you will get a wrong graph if you impose them. This means that Y as a function of X is like MPG squiggly to weight and then MT cars. So you can see that I did an LM, I did a linear regression, I did a GG plot here to see if the model makes sense. This is what I got when I do the GG plot. It's not as good as the other one. It's not as good as the Afghanistan example. You can see that the reason why I wanted to include this is I wanted you guys to see what happens when you have wide confidence bands. You can see here the confidence bands are kind of wide at the bottom. That's because you have sparse points over here and the line did worse over here. It did better over here. So you have tighter confidence bands, but it did pretty poorly over here and over here. So you can see that that's why you have wider intervals over here and here, but it's kind of tight here, right? So I just wanted to point that out. And so you can see that it's giving you a line of best fit, and I probably could still use a linear regression model, but the significance will not be as good as what I saw in the previous example. Let's confirm it. So if I do a summary of my model, yeah, you can see that the significance of the intercept term is now only to -10, where it was the -16 in the previous example. You can see visibly it's not as good in your plot. That's why the significance, while it's still significant, it's not as good. Notice that in the previous one here was the -16. It's the -10 here because obviously the relationship is not as strong. It's still significant. We would still say that it appears that the miles per gallon is increasing. Like you use more as your weight is increasing, or no, sorry, you use less, the weight increasing. It's opposite relationship. So this is actually negative. Let me see. This is a negative relationship. So you can see that it's still significant in the sense that your MPG goes down as your weight increases. So the miles per gallon, like how far you can go, is going down as your weight increases. That kind of makes sense. So you can probably travel less if your car is too clunky. So there's a negative correlation as the one increasing, the other one is decreasing. So if your weight increases, how far you can go if your gallon is just less, right? Which intuitively kind of makes sense. You probably can't go as fast when your car is clunky and heavy, right? That's what it's really saying. It's still significant, but to a lesser extent. So you would probably do this hypothesis test in your assignment, right? So he might ask you, do you think your relationship is significant? You only have a significant relationship if your p-value is less than 0.05. Please note this. If your p-value is big, your relationship is not significant, which means you are governed by the null model, which I think I specified to be. I might have to leave it. I might have to leave it. Let me see. I might have deleted my null model. Anyways, the null model would just end up being, MPG is equal to beta naught plus, right? You would have no relationship with weight. So the null model always is a slope parameter like 0, which obviously we don't want to happen. But if your p-value is big, you essentially have the null model. Null model, you cannot predict your y by x. So be mindful of this for your assignment this week. But I think this assignment this week should be somewhat, I guess, intuitive, maybe. The only thing to check for is your joining. Make sure you're careful about the inner join and left join. That's it. I will post this to my